So on Friday we left off and we were talking about standing waves, and we looked at standing waves on a spring. Okay, so one-dimensional standing waves. Okay, and we said that standing waves occur because of repeating patterns of interference. Okay, so they go to one end, they reflect off that end inverted, they come back, the source keeps making waves. All that wave energy stays in the medium, and you get areas of constructive interference and destructive interference because all the waves have the same wavelength, they're traveling at the same speed, they all have the same frequency, so they keep meeting up at the same places. Ready to recall that from Friday? Okay, so what we're going to look at now, instead of that on a string, like in a string instrument or something like that, now we're going to look at it in terms of a column of air. So basically how all wind instruments work. Okay. Now, some string instruments also use a vibrating column of air in order to naturally amplify the sound that they produce. Okay. That would be things like guitars, a bass does a similar thing. Even a banjo, okay, it's almost like a banjo is almost like a guitar and a drum put together. Okay. When you pluck the string, the sound waves actually hit a skin that's like the skin of a drum, and it makes the column of air behind it vibrate, as I understand it. Someone can correct me if I'm wrong. Okay, which is why it makes that kind of twangier sound than a guitar does. Okay, and of course there's things you can do to make different instruments sound different. Like a ukulele always sounds happy just because it has a small column of air and short strings, okay, that it uses to make sounds. You can't produce as deep a sound on a short string as you can on a long string, which is why a bass is longer. Okay, and the dudes that play it are totally chill. Okay, I don't know why that is, but it just seems to be a pattern. I've never seen a bass player who's like. They always just seem like the chillest guy in the band. Okay, so the longer the column is, okay, then the lower the frequency of the sound that's going to be produced. Okay, so we're going to look at two different types of air columns: open air columns, which are open at both ends, and closed air columns, which are open at one end, okay, and closed at the other. Yeah, I know they're technically both open at least at one end, but one is closed at one end, so that's closed. Okay, so we get the air columns, okay, to vibrate, which basically just means that as long as the column is the right length, we get sound. Okay, at certain lengths we get loud sounds, and at certain lengths we get almost no sound at all. Okay, and everywhere else is kind of in the middle. Okay. All right, so let's have a look at first, okay, our closed air column. So in a closed air column, a standing wave pattern is formed that always has a node at the closed end. Okay? Why is there always a node, do you suppose, at the closed end? What would be happening to the waves then?
Reflection.
They'd be reflecting. Just like on a string, okay, they're going to reflect off the fixed end. Well, a closed end is like a fixed end. So the waves get there, they reflect off of that end, and they come back, and you get a standing wave that you can't see because it's in air, okay? But you get that standing wave forming inside the column of air. Now, the thing with closed air columns is that is a lot different than how open air columns work, right? So the first, let's say, loud sound or antinode that I would hear with a closed air column happens when the length of the column is 1/4 of the wavelength, because an antinode is 1/4 of a wavelength from the node. Okay, everybody with me there? Right? And then if I lengthen the tube for that same frequency of sound, I would get another loud sound at 3/4 of a wavelength, okay? Because the antinodes are a half a wavelength apart, okay? And so on and so on. So every half a wavelength, I get a louder sound, okay? Which means that closed air columns can only produce a lower range of sounds than open air columns, which is why very few instruments are closed air columns. Okay. The most common old school instrument that is a closed air column is blowing across the top of a bottle. Okay. If you've ever done that, you blow across the top of a bottle, it makes a sound. Depending on how much liquid is in there, you get a different sound. If you haven't noticed that, next time you buy a bottle of pop, you can try it. Okay. Try it when it's full. It'll be very high frequencies. Okay. As it gets lower and lower, okay, or gets less and less pop in it, the air column gets longer and longer and longer and produces a longer wavelength with a lower frequency. Okay. Same thing is true if you've ever run your finger along the top of a crystal wine glass. Okay, and you can make the crystal hum. Okay, what's actually humming, I mean the crystal is humming, but the air column inside the goblet is what's actually resonating. Okay, so as you run your finger along the top of the wine glass, you create sound waves that go into the column. They reflect off the fluid inside, which acts as the closed end, and the sound waves come back out. Okay, depending on the length of that air column, you get a different frequency of sound. Okay, there's actually people that can like play songs. They'll have a whole bunch of glasses and they'll just keep going along and hitting different ones. They can play music on them because they can play all these different frequencies. You have to have a lot of time on your hands, I would think, to bother practicing something like that, but maybe it gets you on America's Got Talent or something, I don't know. Okay, so let's have a look at how this would work. Now, these leak really badly, despite all of our best efforts. So I no longer put it up on top of the desk. I used to put this up on top of the desk to do this demo, and then one day, as I was getting ready to do it, or actually I was finishing, I picked it up to take it off, and guess what happened to the cork in the bottom? Yeah, where did it get me? It looked like I'd wet my pants. It was very embarrassing. So now I do it on the floor, because now there's no chance of that. The floor can get wet, but I can't, so that's good. All right. Can you hear the sound coming out of it right now? Listen to the frequency of it to get close to the top. Did frequency get higher as it got closer to the top? Yeah, because the column of air was getting shorter, right? Okay, I want to make sure I got just enough in there. This is always when it goes wrong.
That's what it sounds like when you're filling up your car too.
Yeah, yeah, you can tell when you're getting close to
Yeah.
the top. Although you shouldn't really have your face close to that when you're filling. It's not a good idea. You'd be inhaling the fumes and stuff, which is not good. Okay, I am going to pick G. What frequency is G, man, people?
It's a bit less than 420 hertz.
It is a bit less than 420. It's 392, actually. No one ever knows that. I don't remember them. Okay, so here's what we're going to do. I'm going to get this thing producing a sound with a frequency of 392 hertz. Okay, and I'm going to use that to see if we can calculate what the speed of sound in this room is. Okay, so 392 hertz is going to be my frequency. And using this column of air, I'm going to be able to get the wavelength of the sound by measuring how long the tube is when I get this, this, and this, hopefully that. I might get 3, okay, in here. If I measure those lengths, then I can get the wavelength from those lengths. Everybody okay with that? If I know the wavelength and the frequency, can I calculate sound? Or speed, sorry? V equals F times lambda, right? So that universal wave equation is going to come back into play with this. So Ethan, I'm going to need you to read what the ruler reads, okay, where the water is.
Right now?
No, when I get a loud sound, I'll hold it still, and you just tell me what the length is.
About 22 and a half.
It's what? 22 and a half?
Yeah.
Okay. All right, so this one was 0.225 meters. Did you guys hear the sudden increase in the amplitude of the sound there? Okay, so I found this antinote. So that 22 and a half centimeters should be 1/4 of the wavelength of the sound. Everybody with me on that? Okay, I'm gonna find the next one. The next one should be 3/4 of the wavelength.
About 65 and a half ish.
That's good. It's 3 times longer than that one. Okay, And that means we should, it's gonna be close, be right near the top. I might actually need to stand on something. Well, we'll see. I think it's there.
110.5. Like 110.
That's exactly 5 times the first number. See, this physics just works. That's what's beautiful about it. 110.5, you said, right? Okay. Now, you could distinctly hear the different amplitude, or the different antinodes there, right? Like it definitely got, and you get more and more of those depending on the wavelength of the sound you get. So if I use C, it's 523 hertz, okay? Would I get more of those? Would they be closer together? Because this frequency would have a shorter wavelength, that's why it has a shorter fork. Okay? In case you see them side by side, right? Like the one that produces a higher frequency has a shorter fork, because it makes a shorter wavelength. Okay, so if we hear it on this one, right? Like it just noticeably gets louder. Now, were there also dead spots? Yeah, like there's a few where it gets almost silent. Oh, I didn't get it very good there. And there's a dead spot. All I can hear is the fork. Okay, so that would be when I pass a what? A note, just a note. Yeah, a note is a place where all the destructive interference occurs. So that's where I don't get any sound at all. Okay? Learn my lesson. Oh, it's still slippery though. Okay, everybody walk up here but me. I'm the only person who falls. All right, so when we got this one, we said that this length was equal to 1/4 of the wavelength. So if I want to find the actual wavelength, what do I do with that number? Yeah, multiply it by 4. Okay, so yeah, that should be 110, right? I think, if my math is right. Yeah, yeah. Okay, and the 0.655 represented 3/4 of a wave. Whoop. Go back over there. Okay, represented 3/4 of a wavelength. So 0.655 equals 3/4 times lambda. Then all I have to do is divide both sides by 3/4, and then have lambda. So oh, we botched that one. We better double check that. Well, we weren't that far off. Weird. Never had one that worked out like that, but this one worked out perfect. The 5/4. Oh no, it didn't. No, that one's way off for 5/4. Let's try them again. Let's try them again real quick, because it usually works better than that. Actually, yeah, because it's supposed to be 1/4. That's supposed to be 3/4. Wait, 0.225 times 4 is not 1.10.
No.
No, it's 0.8 something, isn't it? That was my mistake. I think we're okay, actually. I think we're okay.
Okay.
Let's go back. It's just because Coderre did mental math on a Monday morning. He shouldn't do any day of the week, but he did. Okay, let's try that again. Come on, calculator. 0.225 times 4. 0.9. Oh, These are working better. Okay, so, sorry, 0.9. They're gonna be good. Okay, 0.655, okay, divided by 3/4, we got that to be 0.87, which is nice and close. Okay, and if I do the 1.105, if I say that 1.105 equals 5/4 of a wavelength, so if I divide that by 5/4, which is 1.25, I should get around that same number. .884. So nice and close. They're all really close actually. Okay, so I'm just going to average those numbers. Okay, so I'm going to take that number plus 0.9 plus 0.87 divided by 3. Okay, so 0.885. All right, so our average wavelength is 0.885 for that tuning fork. Okay, and we know that that tuning fork has a frequency of 392 hertz. Everybody okay with that? So if I want to calculate the speed of sound in this room feels like it's about 24 degrees already. It's close as 23 in here. Okay, so it's 23 degrees in here right now. So according to this formula, just to see how accurate we are, the speed of sound in here should be 345, 346 meters per second. Okay, if we take the numbers we had, okay, our 0.885, and multiply it by the frequency of the tuning fork we were using, 392, it's not too shabby. You start accounting for differences in altitude and atmospheric pressure, and that puts us pretty much on the ball. Okay? Everybody with me there? That's the kind of thing I might ask you to do on a test. Okay? I tell you that you've got an air column and it's resonating with this frequency and it's this long. Okay? Calculate the speed of sound. Okay? I'd ask you to do something like that. Or I might ask you to calculate what the frequency would be if the speed of sound was this and the air column was this long. Okay? Then you calculate the frequency. Everybody all right with that? Okay. Now, here's the thing with the closed air columns. Okay? The closed air columns are only going to make sound, okay, at certain frequencies. This is its first frequency that it makes sound at, F1. Okay, that's the fundamental frequency. The next time it makes a sound, it's 3 times longer, not 2. Okay, we learned with standing waves that if I'm making a standing wave pattern and I shake the spring at 10 hertz and then I shake the spring at 20 hertz, that's when I get the next frequency or when I get the next standing wave pattern. But that doesn't happen here. I don't get another standing wave until F3, or do I? Okay, I got 1/4 of a wavelength and 3/4 of a wavelength. What's happening when there's half a wavelength in that tube?
Quiet.
It's quiet. There is a standing wave in the tube. It just doesn't make sound. Yeah, so at F2, okay, what we would have at F2 would be this. That would be F2. There'd be a standing wave, it's just not going to make any noise. Okay? There's actually a standing wave in the tube, it just doesn't resonate at F2. And the same is true at F4. At F4, I'd have a full wavelength in the tube, I just don't hear anything. Okay? So our closed air columns only resonate at odd numbered frequencies. Okay? And that's an important thing for us to remember, because they very often ask on a unit exam a closed air column question, and then I say, calculate the fundamental frequency, so you calculate F1, okay? And then I say, what's the next frequency you would hear? Okay, and everybody just goes and multiplies it by 2. when they should multiply it by 3, because you don't hear anything at F2. You hear it at F3. Okay? Only with closed air columns. Open air columns resonate at F1, F2, F3. They get antinodes in all of them. Okay? They're much more diverse in their ability to resonate. All right, everybody okay with that? We're going to work on some problems just so you get some experience with the kind of thing I would ask, but okay, that's where we're headed. Okay, so the formula you're going to get for closed air columns is this. That lambda equals 4L. That formula is on your formula sheet. Okay, that is for F1 on a closed air column. So when an air column is resonating at its fundamental frequency, okay, it will have 1/4 of a wavelength in the tube. So if you know the length of the tube, you can calculate the wavelength. Okay, everybody all right with that? Now, if you have an open air column, okay, the reflection is not off the end because it's open at both ends. So when an open air column, the reflection is actually on the insides of the pipe or the tube. Okay? And what happens is you get a standing wave pattern at all frequencies. 1, 2, okay? So at F1, I would have, how many wavelengths is in the tube here at F1?
1.
Half. Yeah, there's only half. If I put these two ends together, this is what I get, right? Right, there's 1/4 and 1/4. So there's 1/2 a wavelength in the tube at the fundamental frequency. Okay, the next frequency you would hear, how many wavelengths are in the tube now? 1. Half a wavelength apart, right? Okay, every half a wavelength, I get another standing wave. Okay, so that's where we get this formula from for open air columns. Okay, at the fundamental frequency, the first sound that that column will make, there's going to be half a wavelength in the tube. So the length of the tube times 2 will give you the wavelength. Okay, so that's for F1 on an open air column. So while the formula is on your formula sheet, you have to remember which one goes with which. Okay, so lambda equals 4L, goes with the closed. Lambda equals 2L, goes with open. Okay, questions on those? We're going to go over a few examples here just to get a chance to work on them and see how they work. I don't like the way that one's worded. Okay, let's do this one together here, guys. So this one's actually in your book, so you don't need to copy it down. Okay, so I have a closed air column, and it resonates with a fundamental frequency of 256 hertz. If they tell me fundamental, I know I can use 4L and 2L. Okay, those only work for the fundamental frequency. Okay, and you're only going to get questions that involve that. Okay, so its fundamental frequency is 256 hertz. Okay, they tell me the speed of sound is 343 meters per second. Okay, they want to know the length of the air column. Okay, so L equals the question mark, but we do know this, that lambda equals 4L, because this is a closed air column. What can I calculate right now with F and V? I can calculate lambda. They give me enough information to calculate lambda. So, 343 divided by 256 will give me the wavelength of the waves. Whoop. Okay, so in this case, the wavelength is 1.339 meters. Okay, so now that I know the wavelength, can I calculate the length of the column?
Yes.
Okay, so now I go to this formula. Since I want the length, what do we do with the 4? Divide both sides by 4. Because after all, that column is only going to have how many wavelengths in it? 1/4. Actually, I'm going to use the whole number there. Okay. That looks like the answer I've got up on the board, right? 0.335 meters would be the length of that column of air. Okay. So the only real kind of variations on this are going to be, you're either going to calculate the length, or you're going to calculate the frequency, or you're going to calculate the speed. Okay? But you're going to be given the other things. You're either going to be told how long the air column is, okay, and given like the frequency, okay, or you're going to be given the speed and the frequency and be asked to calculate the length of the two, okay, or you'll be given the speed and the frequency and asked to calculate the wavelength. Okay, everybody with me there? All right, so you do have to use the universal wave equation, and you have to use it in conjunction with either lambda equals 4L or 2L. So, oh, that's bad luck. Okay, should have thought of that before I made that question. Okay, what's different about this one? It's open. Okay, so this open air column resonates with a fundamental frequency of 256 hertz. Okay, same as the last one, 256 hertz. Okay, what's the length of the column if the speed of sound is 341? Okay, lambda equals 4L or 2L? 2L, because now it's an open air column. Okay? And that's really the extent of the trickery that can go on in a question like this. Is it open or closed? Okay. All right. So on this one here, if we're going to find the length, we need lambda. Okay? And we can find lambda because once again, we have V and F. So it's the same manipulation as the last time. We're just going to use 2L, okay, instead of 4L. Okay, so I get 1.332, okay, as my wavelength there. Right. Meters, and then I go to this formula here to calculate the length. So lambda over 2 will give me the length. If I divide that by 2, I get that number. Okay. All right, is that making some sense? Okay, I'm going to make one up that's kind of like what you're going to see on your unit exam. Okay.
For the one that doesn't have the wrong answer.
Yeah, well, hopefully it won't, because I'm just going to pick numbers out of my head here. give you a couple minutes on that one. What kind of air column is it? Closed. Okay, so we know right away that lambda equals 4L. Okay, because the only frequency it's going to produce when you blow across it is this fundamental frequency. Okay. How long is the air column?
11 centimeters.
11 centimeters, that's the trick. Okay, got to watch out for something like that. Remember, liquid doesn't count. The liquid doesn't resonate. It actually acts as the reflective surface. So the length of the column is 0.11 meters, right? What do I do with the 18 degrees Celsius? Use it to find the speed. Okay, so 342.8 meters per second. Okay, what can I find right now that will help me find the frequency? Lambda, yeah, I can find lambda because I know the length of the column of air, and I know that lambda equals 4 times that length. Okay, so that means then that lambda equals 0.44 meters. Okay, 4 times the length, 4 times 0.11. All right, now that I've got lambda, can I find f? Okay, so v equals, and so we're looking for f, so we'll have v divided by lambda equals f, so that'll be 342.8 divided by 0.44. Okay, so our frequency is going to be, we only have 2 significant digits here, so 7.8 times 10 to the 2, 10 to the 2 hertz. Okay, now, part B of this question. What's the next frequency this water bottle could produce? I would times that by 3. F3 is the next frequency of sound it would produce. It will produce no sound at F2. Okay, so this is that trick I was talking about earlier.
So would the question say, like, what's the next frequency you can hear?
You could hear, or that would be actually like audible,
Yeah.
produced, because you don't produce any sound technically at F2. You produce a standing wave, but no sound. And that's pretty technical. So I would probably say audible, or what's the next frequency you would hear?
Yeah.
Yeah. Okay, so 3 times that number would be the next frequency of sound that that could produce.
Just have a question about significant digits. So let's say that 18 was a little higher than 22 centimeters. Like even though we change it to meters, would we still use that as significant digit?
When you convert it to meters, you don't affect its measurement.
Oh,
It's still 0.22, it's still 2 significant digits, right? So you don't affect its measurement by converting it from one set of units to another. Okay, now, if I had like the part B of this, okay, I would use that rounded value, not the non-rounded value. Okay, remember that, because it actually can make a difference. If you use the whole value, sometimes it pops it up an extra hertz or 2, okay, when you're multiplying it by 3, and then you would get it wrong because you didn't use the rounded value. So make sure you use the rounded value. All right, I would like you guys in your digital workbook here to try a few of those. Okay, I'm just gonna pick a few here for you to try, because I don't think we need to do them all, but we need to do a few of them at least. Okay, so I would like you guys to do two, 4, 9, 10, and 13. Okay, so 2, 4, 5, 9, 10, and 13 are the ones I would like you working on. Yeah, that way you got 3 closed, one that asks you to calculate length, one that asks you to calculate wavelength, one that asks you to calculate speed, okay, and same deal for the open ones. Yeah. When you can go back.
Can you pull it down?
Oh, so you can see the top one? Okay, those are in the digital workbook. You can call them up on your phone, guys, if you can't read them up there. Okay, so at number 10, we have a open air column. Okay, so we know right away lambda equals 2L. Okay, and it's resonating at a fundamental frequency of 384 hertz. What's the frequency of the next harmonic it'll resonate at? Okay, next harmonic that an open air column will resonate at is F?
F2.
2. Multiply that number by 2, 768. Yeah, it's one that often gets overthought, because it seems like it should be more than that, but that's all it is, yeah.
Can you go for 13?
Mm-hmm. Okay, so we're looking for length on this one of an open air column, so lambda equals 2L. Okay, produces a fundamental frequency of 256 hertz at 20 degrees Celsius. Okay, 344 meters per second. Okay, is our speed. Since we have V and F, we can calculate lambda, V over F, 344 divided by 256. Okay, so we're looking at 1.343 meters as our wavelength. And since we're looking for the length of the column, it'll be half that, so we'll divide it by 2. Okay, 0.671. Okay. Oh, I got 0.670 there. Oh, I think that was with the old. I gotta correct that, sorry. This used to be 331. All right, yeah, so if you got 0.671, you're okay. Yeah. What's that? Or 0.672, yeah. Sorry, yeah, 0.672. We got 0.672, you're good. You did it right. Okay, any others? All right, so tomorrow, okay, we are going to be going over the Doppler effect, okay? And that's, it's pretty straightforward. The formula is a bit of an algebra challenge, okay? But the concept itself is pretty straightforward. And I'll have a little demo for that as well. The Doppler rocket will be sent back and forth. It's a very cool name for something that's not very cool at all. Okay, we'll send it back and forth across the room, and we'll hear it shift, okay, in frequency.